Podcast 22, Motion Graphs. So we often use graphs to allow us to visualize the movement of objects. So recently we've been doing work on terminal speed and falling coffee filters, and the graph below we've seen before. This graph of speed against time shows us how the speed of the coffee filters changes with time, eventually reaching a terminal speed. Without this speed time graph, it would be a little harder to explain how the motion of the object changes with time. We can clearly see that the object's speed is increasing, it's accelerating, but the rate of increase drops off, and finally we don't have any increase in speed at all, and that's what we call the terminal speed. We can use graphs to represent any kind of motion, so let's look at another example. So here's the surface of the moon, and we have an object falling on the moon. The reason I've chosen that is because there's no air on the moon, so we've got no air resistance to worry about. So what will the speed time graph look like for this example? So here it is. We've got the speed and the time, and in this case we see the initial increase in speed doesn't change. In the previous example it changed and eventually we had a terminal speed. But in this example the object simply keeps on speeding up and will only stop when it actually hits the moon. So the rate of increase in speed we could say is constant. The slope is constant. So that was the object's speed and how the speed changes with time. Now let's think about how the distance traveled by the ball relative to its starting point changes with time. Let's think first. Now the ball is accelerating due to the moon's gravitational pull, which means its speed is increasing. Speed is distance traveled per second, so if the speed's increasing, the ball must travel further with each passing second. Let's see how that looks. So here's the graph, distance against time, and we see we've got an upward curve. An upward curve. The fifth second here, we can see that the ball doesn't travel very far in that increment of time. But here the 15th second, same increment of time, but the ball is now traveling much further in the same amount of time, showing us that it's actually increased its speed. It's traveling more meters per second here than down here. Finally, let's consider what's happening to the ball's acceleration. Well, the resultant force on the ball is just the ball's weight. There's no air resistance to worry about. So the only force the ball is experiencing is the weight downwards, and that doesn't really change. It remains constant, so the acceleration must be constant from F equals ma, Newton's second law. If the force is constant, the acceleration is constant, assuming the mass is going to remain the same. Let's have a look, see how that looks. So the acceleration isn't changing with time, it's remaining constant as the time goes by. So we see a horizontal line. So just summarizing those three graphs. The first graph, distance against time, we can see that we have a slope, an increasing slope in this graph. This is for the falling object with no air resistance. The second graph, speed against time, we can see that we have a proportional relationship, a straight line graph through the origin. And the third graph, the acceleration time graph, we can see we've got a horizontal line showing that the acceleration is remaining constant. What I'd like to do now is to try to link some equations of motion, some of which you may know, to the graphs and show how they fit in with each other. So most of you will probably already know that speed is given by distance divided by time. Speed equals distance divided by time. It's the distance covered per second. So speed is in meters per second. So let's see how that equation fits in with the graph. So this is the first graph, distance against time. Distance against time. We have distance and time here as well. In fact, the slope of this graph is distance divided by time, rise over run. So the rise over run of this graph is distance divided by time. So all that said, the slope of the graph gives us the speed of the object. The slope of the graph gives us the speed of the object. Now we can see that the slope is increasing, it's getting steeper, so the speed is increasing as time goes by. You may also now know that the acceleration is the rate of change of speed, the rate at which speed increases. So when you drop something, its speed increases, and that's given by acceleration. Acceleration at the surface of the Earth is around 10 meters per second squared, which means each second the object increases its speed by 10 meters per second. It's the change in speed divided by time. So let's see how that equation fits in with the second graph. So there's the second graph. We can see that we have speed and time in the same way as we have speed and time in the relationship. In fact, the slope of this graph is speed divided by time. Rise over run, speed divided by time. So the slope of this graph must be the acceleration. So the slope of this graph is the acceleration. Now we can see that the slope is constant here, it's not changing, indicating that the object is accelerating at a constant rate. As we would expect for an object falling close to the surface of the moon or a planet, we'd expect the acceleration to be constant. Finally, another equation, well, it's really just the first equation again, rearranged. So we're going to rearrange speed as distance divided by time and write distance equals speed times time, speed times time. And let's see how that equation fits in with, again, the second graph. So here's the second graph. Speed and time is there, speed and time. Speed multiplied by time will give us the area of this shape, or the area under the graph is speed multiplied by time. The area under the graph is speed multiplied by time, so the area under the graph must be the distance traveled by the object. So all of this also applies if the object is not falling but moving horizontally in a uniform or even in a random way. PHET has got a great applet, a moving man applet it's called, that links the movement of this person and the corresponding graphs. We can see here position time or distance time graph, velocity they've called it here, this is our speed time graph, and acceleration time. So here's the applet. Now what we can do is we can dial in a velocity for the person, like so. We can press play and off they'll walk. And I'll pause it there. What we can see is the distance time graph is a straight line. Remember, the slope of the distance time graph is the speed. Now because this is a straight line, it's telling us that the speed is constant. We know it's constant, it's down here. On this graph, the speed time graph, we can see a horizontal line which is telling us that the speed is constant. And if the speed is constant, of course, the acceleration must be 0. I'm going to reset that now. And this time I'm going to dial in an acceleration. Not too quick. Acceleration. There we are. And I'm going to press play and see what that looks like. And pause just before they crash into the wall. Not quite quick enough. So here we can see the position or distance time graph is an increasing slope, just as we saw before. This is telling us that as the slope is increasing, the speed must be increasing. This graph here, straight line graph with a constant slope, showing us that the acceleration is constant. We know it is because we put it in here. And the final graph of acceleration time, we can see that the acceleration is constant, so we're expecting to see a horizontal line with no change in acceleration. Resetting this once again, I can just show you what happens if I actually click the man and move him around, moving to the left, moving to the right. We can see the graphs now look very different to how we've seen before, but one thing remains the same. The slope of this graph is the speed at any particular time. The slope of this graph at any particular time is the acceleration. And the area under this graph gives the total distance moved from his original position. So in summary, we can represent the motion of an object using distance time, speed time, and acceleration time graphs. The slope of a distance time graph is the object's speed at a particular time. The slope of a speed time graph is the object's acceleration, and the area under a speed time graph is the distance moved by the object.